In this video, we concern ourselves with a problem of balancing a faceplate. So let's have a look at the problem. We have two weights, one of 1.5 kilograms, we denote it by the symbol A, and this has an angle of 135 degrees and a radius of 100 millimeters. The second one, B, is of 2 kilograms and the angle of the angle is 30 degrees and the radius is 80 millimeters, and we want to balance this system by using a single mass of 3 kilograms, and we denote it by C. We want to calculate the position in which the balancing mass needs to be fixed. You can see here we have A, which forms 135 degrees. Alright, then we have B. This angle is 30 degrees and the radius of A is 100 millimeters and the radius of B is 80 millimeters. So we are looking to find where to place this rectangular weight. Alright. This problem is important because balancing the faceplate is really important, because if we do it in the correct way, then we avoid vibrations, which will cause problem to the faceplate, and also we preserve the faceplate in order to function for a long period of time. Because if the balancing is not done correctly, then there are additional vibrations when the faceplate is rotating. There are vibrations which will cause problems in the long term for the faceplate. So the first step that we need to do here is to write what we know. We know the mass A is 1.5 kilograms. The angle is 135 degrees and the radius of A is 100 millimeters. For the second body, MB equals 2 kilograms. The angle is 30 degrees and RB is 80 millimeters. And of course we know the mass of C is 3 kilograms, the ones that we need to balance the faceplate. Alright, what we are looking for, we look for RC, the radius, for C and the angle. We will solve the problem using the analytical method. So the first step we can do is to convert the coordinates, the polar coordinates, to rectangular coordinates. So what we have here in the figure below, in the previous figure, was the following. We know where the B is, so this has a radius B and angle theta B. And we know also where the mass A is, where the weight A is, and this is RA and theta A. This is a polar coordinate system. So this is a polar coordinate system, and we need to convert it, we can convert to Cartesian coordinate system. So the x coordinate for the weight A should be the radius times cos of the angle theta A. So the radius of A is 100 millimeters times cos 135 degrees, and here you do the calculations and you get that XA coordinate is minus 0.0707 meters. I have converted to SI units. So the XA coordinate is minus 0.0707. Now I can convert also and find what is the Y coordinate. YA coordinate is RA times sine theta alpha so this is 0.1 times sine 135 degrees, and this gives me 0.07071. Let's put this one also in a box. 0.7071. So my pair is XA YA equals the X, I know the X coordinate and I write down the X and the Y coordinate. We do the same for the body B. We do the same thing. We calculate the X coordinate. So it's RB times cos theta B. The RB is 80 millimeters times cos 30 degrees, and this gives me 0.069282 meters. This is my X coordinate for B, and YB equals RB times cos theta B is 80 times sine 30 degrees. So what is YB is 4 times 10 to the power of minus 2 meters, or you can write it like this as a decimal, 0.04. So I write down my pair. Now I can use this to draw a Cartesian coordinate system. Cartesian coordinate system. So XA YA should be here. XB, YB should be here. This X and this is Y. Here is to make it a little bit more visual. This is why we create this diagram. Then step 2, we define the centrifugal forces for A, B and C. So let's have a look. So we have, this is the X force in the horizontal axis, FAX, and this is FA of Y. And here is the magnitude FA. I will explain a little bit here. And this is the angle theta A. So for body A, so FA equals the square root of FAX squared plus FAY squared. I use the Pythagoras theorem, what I do here. So here is a 90 degrees, I have a right triangle, so I use the Pythagoras theorem. This is FAX and this is FAY, the two vertical sides. I square them and take the square root to find the hypotenuse here. So FAX, the FAX equals MA times RA, the mass times the radius times omega squared, which is the angular frequency, times cos theta alpha. This is the force, this is a centrifugal force in the x direction. And FA of Y equals MA times RA omega squared sine theta A. This is the force in Y direction. So I denote this, I need these formulas here, 1 and 2, because I will use them later on. Now for body B, I have FBX, FBY. These are the two vertical components of the force, and I also have FB. Like before, for the magnitude FB, I use the Pythagoras theorem. To calculate this length. So it should be FBX squared plus FBY squared. And then I define the horizontal and vertical forces. FBX equals MBRB omega squared cos theta B. FB of Y MBRB omega squared sine theta B. This is relationship 3 and this is relationship 4. I also put them in a box. And I do the same thing for C, for body C. This is FCY, FCX. And this is the magnitude of the force. This is FC. FC equals the square root of the sum of two vertical sides squared. So it's FCX squared plus FCY squared. FCX equals MCRC omega squared cos theta c, and FCY equals MCRC omega squared sine theta c. So this is the force in the x direction, and this is the force in the y direction. Now I needed to create two equations. So the first one is balancing the forces in the x-axis, balance in x-axis. So FAX plus FB of x plus FCX equal to 0. In order to have balance, we use Newton's law. All the forces added in the x direction should be equal to 0. We use substitution. Using formulas 1, 3 and 5. So we have MA RA omega squared cos theta A plus MB RB omega squared cos theta B plus MC RC omega squared cos theta C is equal to 0. We can divide by omega squared. We can get rid of omega squared. And we have MA RA cos theta A plus MB RB cos theta B plus MC RC cos theta C is equal to 0. We call this 7. We solve 7 with respect to cos theta C. So cos theta C equals minus MA RA cos theta A plus MB RB cos theta B divided by MC RC. This is equation number 8. Now we also need to balance in the x direction. Balance in the y-axis, sorry. In the y-axis. The forces in the y-axis, if we add them together, should give equal to 0. Now we use substitution. Using the formulas 2, 4 and 6. MA times RA omega square sine theta A plus MB RB omega square sine theta B plus MC RC omega square sine theta C is equal to 0. We can divide by omega squared. We have MA RA sine theta A plus MB RB sine theta B plus MC RC sine theta C is equal to 0. We call this equation number 9, and we solve 9 with respect to sine theta. From here we have sine theta C equals minus MA RA sine theta A. So I have these quantities are in brackets, plus MB RB sine theta B divided by MC RC. This is number 10. Now using 8 and 10, we can find the tangent of theta C. So tangent of theta C equals sine theta C over cos theta C, and this is MA RA sine theta A plus MB RB sine theta B divided by MA RA cos theta A plus MB RB cos theta B. And from here, theta C is the arctangent of this quantity here. So this is formula 11. Now we will use this formula to calculate what is theta C. So what we do is substitution. Arctangent, I rewrite the formula. And I do substitution. So I have to plug in the numbers. I have converted the lengths into meters because you don't have to, but I do it because I want to have all the units in international system of measurements. So it's 1.5 times 0.1 sine 135 degrees plus 2 times 8 times 10 to the power of minus 2 sine of 30 degrees. And basically I have the cos in the denominator, so I have 1.5 times 0.1 cos 135 degrees plus 2 times 8 times 10 to the power of minus 2 cos of 30 degrees. Now if you do the calculations, what you get is arctangent. So you do the calculations and you get in the numerator 18.60 3.65 and in the denominator 3.2495. So if you use your calculator, if you do this division here, is 5.72596. You use your calculator and you get that the angle is approximately 80 degrees. So the angle is approximately 80 degrees. Now the final step, step 3. For step 3 we need to calculate the resultant force. We calculate step 3. We calculate the resultant force. So the resultant force is we use the Pythagoras. We find the FA squared plus FB squared. So we need to calculate first what is FA. We need to calculate what is FA, this length, and FB, the magnitude of these forces. FA equals MA times RA. And this gives me 15 times 10 to the power of minus 2 kilogram times meters. I have FA and now I have to find FB. Is MB times RB. So it is 16 times 10 to the power of minus 2 kilogram times meters. Now the resultant force equals the square root of FA squared plus FB squared, so it is 15 times 10 to the power of minus 2 squared plus 16 times 10 to the power of minus 2 squared. So this can be written as 10 to the power of minus 2. I can take this common factor, 10 to the power of minus 2 can go outside. And I have the square root of 481. And this gives me that the resultant force Fr is 0.21932 kilogram times meters. Now, the magnitude of Fc should be the same with the resultant. So Fc, the magnitude of the force Fc, should be the same with the resultant force in order to balance the system. And from here, this force is mc times rc. So from here I can specify what is the radius rc by taking the resultant force and dividing by the mass c, by the mass mc. And what I get is 0.073 meters, or rc equals 73 millimeters. So here the FR of course is, we have made substitution to calculate it. Now we know what the radius for C is. Consequently, the radius for C is 73 millimeters, and the body C should be placed at angle theta C plus 180 degrees, because we want the opposite of the resultant force. So it should be theta C plus 180. Theta C is 80 degrees plus 180, 260. Anti-clockwise, of course. Anti-clockwise. So let's draw the figure below. We have here B. This is 30 degrees. This is 80 millimeters, right? Also we have A, which is 1.5 kilograms. It is 135 degrees, so this is 0, 90, 180, 270 degrees. It's 100 millimeters, the radius for A. Now C, 80 degrees is somewhere like here. This one is 80 degrees. So we draw the opposite line here. So this angle here is 260. So we place C here with a radius 73 millimeters. Radius 73 millimeters, angle 260 degrees.